The elliptical orbit of a comet is shown above. Positions 1 and 2 are very respectively the farthest and nearest positions to the Sun. Fun fact, you can call position 1 the aphelion and position 2 the perihelion because 2 and the Sun are paired together. Fun fact. The distance from the comet to the Sun is 10 times farther at position 2 than at position 1. Okay, at position 2, the comet's kinetic energy. Will tell me about the kinetic energy, and the way you can think about this is a skateboarder going up and down inside a ramp or on a ramp, converting kinetic energy to gravitational potential energy and back and forth. Think about it. When you're further away from the Earth, you're further away from the Earth. That means that kinetic energy is a maximum when you are at the bottom of the ramp. When you are at position 2, the maximum kinetic energy is at position 2. A satellite of mass m moves with speed v in a circular orbit of radius r around the Earth. Which of the following is true? We'll take them one at a time. Number 1, to place a larger mass in the same orbit would require a larger orbital speed. Well, there's the equation for velocity, and no, number 1 is not true. The velocity of the satellite depends on the mass of the orbited object, not the mass of the orbiter. Otherwise, as we said in class, the astronaut and her sandwich would not float together. Big M, mass of the orbited, in this case the Earth. Number 2, the centripetal acceleration is independent of the mass of the Earth. There's the equation. Number 2 is not true. The force, the net force, the weight force, the force of gravity to the Earth depends on the mass of the Earth, and F equals ma, that still works. So the centripetal acceleration depends on the mass of the Earth. Force depends and acceleration depend on the mass of the Earth. Not independent. Number 3, the angular momentum of the satellite is constant. There's our equation for angular momentum. What is momentum? We haven't talked about momentum yet, and we haven't talked about rotation yet, and that's a cross product, and this is confusing, but using the almighty process of elimination, the answer is 3, or D. Planet X has an acceleration due to gravity at its surface that is 3 times that at Earth's surfaces. 3g. If the mass of X is twice the mass of the Earth, the radius of X in terms of radius of the Earth is what? Is making my head spin, is a headache. There is Newton's law of universal gravitation, which means that the acceleration due to gravity small g at the surface of a planet is equal to big G times the mass of the planet divided by the radius of the planet squared. And we know that little g on planet X is 3 times 9.8. Putting this stuff down and putting it together, notice we've already substituted in here that the mass of planet X is twice the mass of the Earth. A lot of writing. Write it all out. You got to work quickly, of course, but you write it all out. You won't make mental mistakes. The last thing you want to do is spin your wheels, second guessing something you can't see because it's in your head. Rearrange to solve for the radius of planet X. That's what we want, and the answer is C. Now again, I know what you're thinking. You're thinking, gee, I should be smart enough to just mentally churn that out without having to write down anything. After all, I've got a busy person, I got things to do. No, you got to write it out, especially this step and this fact.